will discuss the construction of, you can hear me?
Yes, ma'am.
So, we will discuss the construction of the induction motor in very shortly. But basically, we have seen that we have basically two types of three-phase induction motor. That is one depending on its rotor connection construction. That is the squirrel cage motor and the wound rotor motor. So both have their distinct advantage and disadvantages. Now, for both the cases, stator construction is similar. This shows the stator lamination of induction motor. Now, stator is laminated because it supply is AC, so flux is AC, so there will be eddy current and its loss, which is inherent with alternating magnetic circuit. So stator is laminated. Now there's a you have studied DC machine. Now DC machine, you have seen the stator. We have the armature field winding. So the stator has the frame. In case of DC machine, the frame itself is a part of the magnetic circuit. The frame, the salient pole fields are bolted, and the flux path is completed to the through the frame. For AC machine, however, this is the stator lamination, and frame is a different construction. Frame is outside this one, which is either cast if it is a small motor, or fabricated steel structure. To the frame, these stator lamination are fixed through this. There are slots through this. We will put the wedges to fix the lamination to the frame. Now, frame there might be some leakage flux in the frames, but it is normally negligible, and the flux path is complete. This portion is the core, and this portion is the teeth. So the flux is mainly completed. Flux path is completed like this. So this frame, which is outside this lamination, is not a part of the magnetic circuit. Now we have a distributed winding, so we will have slots on the stator. Now, in case of induction, either we can have parallel sided slot or parallel sided teeth. Normally, for induction motor, we have parallel sided teeth, and the slot will be slightly trapezoidal in nature. In both the wound rotor and slip ring motor, the stator lamination will look like this. For the rotor, now one is the number of slots on the rotor. Rotor structure is also slotted. Whether either we put the either we put the distributed winding or we put the cage winding in the slots, but both are slotted structure. Now, there are a limitation of slot combination of the stator and the rotor, because say if we have the same number of slots in the rotor and the stator, induction motor have a very small air gap, less than 1 millimeter. It is for smaller motor, it is something around 0.3, 0.4 millimeter. So if the number of slots are the same, then the rotor will have a tendency to get locked in a rotor will have a tendency to get locked for a position where the reluctance is minimum. that also happens if the number of slots of the stator and rotor are integral, multiple, or multiple. So there are certain combinations of stator and rotor slot numbers that should be avoided for good construction. Otherwise, this aligning torque might be quite large, and it causes a phenomena which is called cogging. Now, for full rotor induction motor, stator winding is a three-phase distributed winding. Similarly, on the rotor also, we have a three-phase distributed winding. Now, the number of poles of the stator and rotor winding should be same. However, theoretically, number of phases of the rotor can be different, but normally we have the same phase also. That is the same phase and number of poles for stator and rotor winding. Now, the terminal of the rotor winding are connected to the slip ring, which is mounted on the shaft, and slip ring is connected to the external circuit through brushes. Now, this can be directly shorted, or we can insert resistance in the circuit as required. Normally, during starting, to have a high starting torque, we can insert resistance. Resistance is also inserted if we want to control the speed of the induction motor. Now, for squirrel cage, we have slots on the rotor. In the slots, normally for small and medium size motors, we have die-cast aluminum bars. That is, directly the aluminum bars are cast in the slots, and then end rings, aluminum end rings are welded to these bars. Now, for larger motor, we can have copper winding also. Now, normally for copper squirrel cage winding, copper bars are placed inside slots, which are then shorted through copper end rings. However, now methods are available for die-cast copper winding also, because previously what was the problem is that copper has a very high melting point, so die casting welding copper was difficult, but now methods are available. So if the winding is made up of, rotor winding is made up of copper, obviously the motor size for the same rating will be smaller, and it will have higher efficiency. Now, in the squirrel cage winding, one thing is done. Normally, this rotor slot is not parallel to the stator slot. Instead, it is skewed. That is, it is slightly placed slightly like this. If it is parallel to the rotor shaft, then it should be this one. But instead of that, it is skewed by this figure. It is skewed by an angle alpha degree. The advantage is that if it is parallel to the shaft, then the flux linkage at every point of this conductor. But if it is skewed, it will be different at different points, and at the rotor we have a better performance of the machine. Say for skewing, that if EM is the maximum voltage produced per unit angle of the skewed inductor, that is this one, EM per degree. In that case, at when EM that induced EMF is maximum at this point, that middle point, then at any particular point, say here, where this angle over this small stretch angle del theta, it will be EM cos of d theta. That is, EM per degree is the induced EMF. So into d theta, this is the EMF induced in this section. So the total EMF induced will be minus alpha by 2 plus plus alpha by 2 em cos theta d theta. So it comes to be twice em sine of alpha by 2. Now if it is not skewed, then the EMF over the whole length of the conductors will be EM. So for an angle alpha, it will be EM alpha, the total EMF. So the ratio is term that Ks, the skew factor, is twice EM sine of alpha by 2, that is the EMF induced in the skewed winding, divided by EM by alpha. So this is sine alpha by 2 by alpha by 2. Looks similar to the winding factor we have derived earlier. So the number of turns into multiple by Ks. Now one advantage and disadvantage of two rotor types. Now this one is a picture of shifting rotor. So this is the, here also we can have skewing. So this is the winding, then this is the slip rings, this is the shaft. So the main advantage of slip ring winding, we have seen that resistance of the rotor circuit can control by external resistance, and so we can insert resistance in the rotor circuit during starting or during running according to our needs. But the main disadvantage, it has certain disadvantages also, and for disadvantage only this machines is used, particularly for applications where we require a very high starting torque. And but the main disadvantage is that it is for the similar rating. Slip ring motor will be more costly than the squirrel cage one, because obviously the slip ring motor, when we have a wound winding, we will have lots more of copper because of the override portion. Then we have the slip rings, so the copper cost is much more. Manufacturing is also complicated, so it is manufacturing cost is also more. So and another disadvantage is that the squirrel cage motor is very rugged because it does not have any moving contact. So it is very rugged, require very little maintenance, because whenever there is a moving contact, it requires the continuous monitoring and maintenance. So here we have the slip ring and brushes, they will get eroded out, so it has to be maintained properly. And moving contact in the electrical circuit, whatever well designed it might be, there will be some sparking. So in some atmosphere, it might not be advisable to have sparking also. So these are the disadvantages. And another thing is that the stator and rotor has to be wound for the same number of poles. For the squirrel cage motor, the main advantage of it is its ruggedness, but the disadvantage is that we cannot control the rotor resistance as easily as we can for the slip ring motor. So that we can once designed, by design we can have certain variation in its starting torque and maximum torque, but once designed we cannot control it. And but the one advantage of squirrel cage motor is the squirrel cage winding is adaptable to any number of poles. That is, if there is a provision of reconnecting the stator winding for two different number of poles, say 2 and 4 poles, then the rotor itself always get adjusted to the number of poles, because rotor induced in the rotor, the EMF which is induced will be induced according to the stator current. So it is possible to have a pole changing motor, while for a slip ring motor we cannot have a pole changing motor. For pole changing, the speed change is always discrete, not continuous. Now for squirrel cage motor, what is done? We normally, that rotor slot is shaped different way. Now to have a better performance, we can have deep bar rotor, one construction called deep bar rotor or double squirrel cage rotor. In deep bar rotor, the rotor bar depth is quite high. So what happens that if we see the leakage flux for this is drawn for the double squirrel cage. So the leakage flux distribution of the lower cage and the upper cage will be like this. So the lower cage leakage flux will be much more, and in case the lower portion of the and this is true for the and this is for the double deep bar rotor. So the lower portion, the leakage flux will be more compared to the upper portion. This is obvious because that it is embedded within iron. So the reactance of the lower portion of the winding of the bar is much more. So initially at starting, when the frequency is at supply frequency, so as the reactance is more, so the current always tries to flow to the minimum resistance path. So current has a tendency to flow towards this upper portion here and this upper bar here, where the inductance is less. So the effect is that initially as the current tends to flow through here, so the effective copper area reduces, so the effective resistance increases. So this uneven current distribution during static is utilized to have a high resistance during static. Now once the motor starts, then the rotor frequency decreases. As it decreases, so the effect of the inductance reduces, and normal running the sleep is very low, so the frequency is very low, so effect is almost if there is no effect of the inductance, so the current will be evenly distributed and so resistance will be low. This is done for deep bar or double squirrel cage rotors. Now depending on that, normally NEMA or the National Electric Manufacturer Association defines certain classes of motor. Now this is class A, this is normal slot. Class B is this deep bar or double squirrel cage variety, and this is class C. Class C is also just a special type of double squirrel cage. Here there is a constriction. You can see that conductor is continuous here. Here we have two different parts and constriction in between, so that increases the inductance of the lower portion further, and this one is only using this upper bar. So this is class D. Now the characteristic will be different for class NEMA class A, that is shown in this figure, and is the for a 4-pole machine develop a normal starting torque equal to 150% of the full load torque and should have a maximum torque not less than 200% of the full load torque. Now the for lower speeds, however, there will be smaller starting torque. These motors are take, however, large current because the resistance is lower. Might be as high as 7 times the full load current. So normally they are started at reduced voltage to reduce the starting current. Now for figure B and C, it is class NEMA class B. Both are deep bar rotor. Here it is slightly bar shape is slightly different, like double squirrel cage. So deep bar and double squirrel cage winding motors of this type have types of slot develop normal starting torque with relatively low starting currents. The resistance is high, so starting current will be high, and can start at full load. So as starting current is low, so they can start at full voltage. Such motors are under class B. Class C motors develop relatively high starting torque with relatively low starting current. The starting current is obtained by the high inherent resistance of the slot. Here starting resistance is much more because starting only this cage will be conducting. So this is class C type of NEMA motor, and the slots shown for class D, that is this one. This is class D. With squirrel cage windings, this motor will have high starting torque because it has high resistance with moderate starting current, which is obtained by using the high resistance of the rotor. But it is as the resistance will not change with speed, so it sacrifices the small operating speed. So the characteristic will be for a high resistance only. It will not shift with the frequency. This type of motors are used for operating electric elevators, electric trains, hoists, etc., or flywheel sets. Now, for double cage winding, approximately we can write the equivalent circuit, approximate equivalent circuit like this. If you remember the approximate equivalent circuit of an induction motor, this portion was absent. So, if it is double cage, we will have two values for starting and running. So, we will have two parallel branches. Now, the characteristic can be obtained like this. If it is a outer cage, then it is a higher resistance. So this is the high resistance characteristic. For the inner cage, this is the normal induction motor characteristic. So these two are added. So this will be the resultant characteristic of the double cage induction motor. Now, which type of motor we should use, that will depend on the application. Then effect of harmonics and rotor and stator slots effect on the speed torque characteristic of polyphase induction motor. Now harmonics, there can be of two types. One is the time harmonics, which is present in the time variation of the press voltage, and other is the space harmonic in the space distribution of the air gap flux caused by the distribution of the motor winding. So time harmonics are introduced by the harmonics in the impressed voltages. Now, if the effect of the saturation is in the following discussion, we will neglect the effect of the saturation. If the effect of the saturation is neglected, the circuit is linear and we can apply the superposition theorem. So the number of so we can say that for the fifth harmonic, the time variation of the impressed voltage is the same as that produced by the sinusoidal voltage, but the frequency is 5 times. Now, what are the harmonics present? Now, as we have a star delta connection, we know that third and the triplet frequency harmonics are absent. Obviously, there is no even harmonic because it is because of the symmetry. The waveform is symmetric, so we can only have odd harmonics, and third and triplet frequency are absent because it is not present in the line voltages of balanced three-phase circuit. So first important one is the fifth, then 7th, then 11th, 13th, 15th, 17th, 15th is absent, 11th, 13th, 17th, etc. Now, same direction as the fundamental, some is the opposite direction. Now, we know that 5th, 11th, that 5th, 11th, 17th, etc. are in opposite to the fundamental, and the phase order of 7th, 13th, 19th are in the is same as that of the fundamental. Now say if we consider the 5th harmonic. Now what is the speed of the rotor? Now the speed is mainly related to the fundamental. So this is the fundamental synchronous speed into 1 minus S1, where S1 is the slip related to the fundamental. Now if we have to find out the slip of the 5th harmonic, then this is the 5 into minus 5 into 2f1 by p. This is the synchronous speed of the 5th harmonic, minus sign because it is in opposite direction, minus this is the speed of the rotor divided by again the synchronous speed of the 5th harmonic. So if we simplify, it becomes 6 minus s1 by 5. This is s5. For the 7th harmonic, we simply can find here, this is same direction, so it is plus. So 7 twice f1 by p minus twice f1 p into 1 minus s1, and it ultimately gives 6 plus s1 by 7. So maximum torque of the machine, if you remember, it will be p is the p v1 square 4 pi f1. Now 4 pi f1 by p, this is basically 1 by omega s. So divided by 2 into r1 plus root over of r1 square plus x1 plus x2 to the power of square, where this is the total inductance, this is the effective resistance of the stator. Now because of the greater frequency, the effective resistance will be much higher for the 5th harmonic. So if it is R1 for the fundamental, it can be say R dashed for the 5th harmonic, which is much more higher. So for the 5th harmonic, we can, the torque expression we can write this. Now say the 5th harmonic present, obviously we know the presence of harmonics in a particular waveform decreases with the increase of order. So say it is k times the fundamental. K is a factor less than 1. So that torque in place of V1, we will have k V1 square divided by 4 pi, frequency is 5f1, and this is the r1 dash plus root over r1 dash square, and this will be, if we neglect the uneven distribution of the change in distribution of the flux due to higher frequency, if we neglect that, then that inductance will be some 5 times the value of the fundamental. So this will be 5x1 plus 5x2 square. Now, so if we assume that k is say 0.1, that is 10% of 5th harmonic in present, then this factor, this factor will be 0.1 square by 5, that is 0.002 as large of that corresponding term of the fundamental. So the value, and then here in the denominator we have this 5 square, these factors. So inductance is quite large. So you can see that the torque developed by the 5th harmonic will be negligibly small. So normally the harmonic torque does not affect the speed torque characteristic. So normally the torque expression what we derive, we only derive based on the fundamental only. However, this harmonics in the impressed voltage will cause harmonics in the current. But due to high impedance, the load component of the stator harmonic current also will be small. The harmonic current component in the magnetizing current is also small. Now consider if the primary leakage impedance drop are neglected, then the impedance voltage is approximately equal to the induced EMF. So induced EMF for the fundamental E1 per phase will be 4.44 N, that is number of turn, KB1 and KP1. This is the breadth factor for fundamental. This is the pitch factor for fundamental into phi M1, or the mutual flux value for the fundamental, into F. Now say we have 10% of the fifth harmonic, then E5 value will be 4.44 N, then corresponding KB5, KP5, the flux will be phi M5, frequency will be 5F. This is 0.1 E1. So this is 0.1. We can put these values here. So approximately 5M5 can be found out to be 0.1 by 5 KB1 by KP1 divided by KB5 by KP5 into 5M1. Now if we consider 5 by 6 pitch winding, that is if pole pitch considered is 180, then 30-degree short pitch winding, then KB5 this factor KB5 by KB5 by KB1 by KB5, this will be about 0.07. So this will be, if we put the values here, this will be approximately 0.28 phi M1. The impedance drop in the circuit is but this one we derived considering that the impedance drop in the circuit is negligible, but for the harmonic except near the synchronous speed. But since S5, this one we derived earlier, 6 minus S1 by 5, it follows that S1 varies from, as S1 varies from 0 to 1, S5 varies from 1 and 6 by 5. Under this condition, if the stator and the rotor impedance are equal, the impedance drop in the stator is about 1/2 the impressed voltage, because here the value will be large, so impedance drop will be large. According to this assumption, SM5 between S1 equal to 1 and S1 equal to 0 is order of impedance drop will be large, so we can consider this as half, which we consider equal to, so it will be 0.145 M1. For such a magnitude of fifth harmonic flux, the fifth harmonic component of the corresponding magnetic current does not produce any significant effect on the operating current of the motor, because that magnetizing current value depend on the flux. So when the flux is quite low, say it is 14% of that of the fundamental, so correspondingly the corresponding magnetizing current also will be low, so it will have very little effect. Now this is as considered the time harmonics. Now there can be space harmonics also. Harmonics in space distribution of the air gap flux. Now, if the impressed voltage is sinusoidal, the speed torque curve of the polyphase induction motor of sinusoidal distribution of air gap is a smooth curve, what we have derived earlier. But in many cases, the actual speed torque curve is not smooth. Some ripples can be seen at lower speed. Some roughness. This roughness is due to odd harmonics in the air gap flux, which are caused by the distribution of the rotor motor winding and by the variation of the permeance of the air gap caused by the slots. Now the space harmonics of the magnetomotive force of the armature coil, what we have derived initially, we have neglected the harmonics, actually that harmonic that MMF distribution. that will be a step one. So as the slot pitch are very small, so with the proper distribution, we can approximate to a sinusoidal distribution. Now that way, when we analyzed, we have only considered derived the equations based on the fundamental, but it will have some harmonics. As the harmonic order increases, the magnitude will decrease. So it will have a series like this. The number of poles produced by the harmonic is equal to the number of poles for which the motor is moved, multiplied by the number of harmonics. That is, try to distinguish for the time harmonics, what we have, the number of poles were the same, but only the frequency was multiplied. So if we have a 4-pole machine, the number of poles remains 4, but the frequency was 5 times for the fifth harmonic. But when we are going for the space harmonics, then it is basically harmonic in the MMF distribution. So if the fundamental create 4 number of poles, the fifth harmonic will create 4 into 5 number of poles. So therefore, the sinusoidal impressed voltage, the revolving harmonic component field in the air gap flux due to the winding distribution revolves more slowly than the fundamental. For example, the fifth harmonic revolves 1/5 as fast as the fundamental. The seventh harmonic 1/7 as fast. There are no third harmonics as it is in a balanced condition, balanced three-phase circuit, and we have 120-degree this phase, so they cancel out. It is true for all harmonics which are multiple of 3. So all the harmonic components fields which exist in the distribution of air gap flux of a 3-phase machine rotate at speed 1/q times that of the fundamental. The fifth, 11th, 17th rotate in the opposite direction. 7th, 13th, 19th rotate in the same direction. According to the Fourier analysis, the MMF of a single coil, nth harmonic is only 1/n as large as that of the fundamental. That is from this Fourier series. This is the form of the Fourier series. For the whole winding, these values are reduced by the breadth and the pitch factor. For example, if the winding is 5/6, pitch is 5/6, the ratio of the product of breadth and the pitch factors of the fifth harmonic and the fundamental for a 3-phase winding is approximately 0.07. This earlier we used. This is the approximate expression we can derive like this. That is KPN. That is the pitch factor is cos n epsilon by 2 and kbn of the distribution factor sin n sigma by 2 by n sigma by 2. Now for fundamental sigma, the phase spread is 60 degree. We have 3-phase winding, so this is 60 degree. Slot per pole per phase. Say Q is equal to 2, so gamma is equal to 30 degree. So short pitching angle is 1 slot pitch, so that is 30 degree. KB1 will be sin 60 by 2 by 2 sin. This is 0.965. KB1 will be 0.96. KB5 will be 0.26 and KB5 will be 0.26. So putting this value, we get 0.07. The slip of the rotor with respect to any one of the space harmonic field is equal to the difference between the speed of the harmonic field with respect to the stator and the speed of the rotor with respect to the stator divided by the speed of the harmonic field. that is the speed of the rotor with respect to any of the space harmonic field is equal to the difference between the speed of the harmonic field with respect to the stator and speed of the rotor with respect to the stator, because there is a relative speed between the stator and rotor itself. So these two speed has to be considered and divided by the speed of the harmonic field. It is, this is the speed of the harmonic field with respect to the stator, 1/5 that of the fundamental. This of the speed of the rotor with respect to the stator divided by the speed of the harmonic field with respect to the stator. So from here it will, we will get 6 minus 5s1. Now F2 for the fifth harmonic will be F1 S5. So 6 minus 5 S1 F1. The slip, similarly we can derive for the seventh harmonic. For the seventh harmonic rotates in the same direction. So S7 will be, putting the values, it will be minus 6 plus 7 S1. The frequency, corresponding frequency, rotor frequency will be F1 S7, that is minus 6 plus 7 S1 F1. Now taking S1 is the slip, so this is very small. Taking say 0.05 the average slip, then fifth harmonic and seventh harmonic fundamental frequency of 50 hertz will be, this will be 287.5 hertz fifth harmonic, and for the seventh 282.5 hertz. Considering the speed of the rotor field with respect to the stator due to the currents induced in the rotor field by any harmonic stator field such as seventh, the speed of the rotor field with respect to the stator is the speed of the rotor field with respect to the rotor plus the speed of the rotor with respect to the stator. For the seventh harmonic field, this speed is the speed of the rotor field with respect to the stator. This speed of the rotor field with respect to the stator plus speed of the rotor's field with respect to the speed of the rotor field with respect to the rotor plus the speed of the rotor with respect to the stator. This is speed of the rotor with respect to the stator. So adding, it will give 2f1 by 7p1. So this is equal to the speed of the seventh harmonic component MMF due to the stator current. This is nothing else. This factor we have used in this expression here. So just the derivation of this. So this is equal to the speed of the seventh harmonic component MMF due to stator current. Seeing that two fields rotate at same speed, they interact to produce torque. Now these two fields produced by the seventh component of the stator MMF wave and the corresponding field created by the rotor MMF wave, they two interact to produce a torque. These two speeds are same, you can see. So they are interlocking, so they will produce a constant torques. In the resultant field moves in the speed 1/7 as first as the fundamental and have 7 times as many poles as the fundamental. It produces fundamental frequency in the stator winding. So basically this is the say normal characteristic for the fundamental frequency. Then for the seventh harmonic, the characteristic will be like this, because this is corresponding to this point, number of poles, the same form, only the values are different. So this is the seventh one, This is for the fifth. So the resultant what we get will be addition of these three. So the resultant characteristic will be follow this, then the fundamental. So there will be a people here. So for some torque characteristic, if it cuts the characteristic here, the motor will try to run at this point. So this since there is an interaction between its phase harmonic in the stator MMF, a polyphased induction motor can be considered to be equivalent to a number of motors mechanically coupled with different number of poles and connected in series in such a way that the phase order of their impressed voltages alternate. For example, if we consider the action of the fundamental in the fifth and the seventh harmonic, just I show here, the motor is equivalent to three mechanically coupled motor with number of poles P1, this one, with number of pole 5 P1. So characteristic is this one, with number of pole 7 P1. So characteristic is this one. The seventh harmonic produces a dip in the speed torque curve of the synchronous. There is a dip in the curve due to the fifth harmonic also, but as the phase order is reversed, so his magnitude is smaller. The dip occurs at a sleep greater than unity. Here maximum dip is here, which is greater than unity. That is not in the motor portion of operation. So certain motors show successive dips at low speed, which make their speed torque curve rough. Figure reference নাম্বারটা ভুল দিয়েছি, 8 হবে না, 8 আগের আছে, this is 10 পরের ফিগার আছে। May cause the motor to crawl at subsynchronous speed. That is, if this is the characteristic and if your load characteristic is like this, say constant torque, the characteristic is like this. In normal condition, the motor should operate here, but here there is a cutting at this point, and this slope is also a stable slope. So motor will try to operate at this point. It is called crawling. Crawling is usually accompanied by considerable noise and noticeable vibration. However, because of small magnitude of space harmonic fields, the torque produced is very also small. This effect can be further reduced by skewing the rotor slot. This is one of the reasons why rotor slots are skewed. We can avoid this phenomenon of crawling. The effect of the stator and rotor slots play an important part in producing irregularities and roughness in the speed torque curve. Okay. Now, these things are a bit complicated, so I will not stop here, and we will again repeat this. Repeat the.
Ma'am.
Yes.
Ma'am, will you share these notes with us or not?
No, হ্যাঁ নোটস গুলো আমি পাঠিয়ে দেবো। আমি একটুখানি সব এডিটের বাকি যেগুলো আছে আগেগুলো একটু দেখে নিই, দু একটা এডিটিং কিছু ভুল আছে, আমি সবকটাই পাঠিয়ে দেবো। দু একটা ভুল থাকতে পারে, কারণ আমার হাতে টাইপ করা তো, আমি এটা সবটাই পাঠিয়ে দেবো। যদিও বই থেকেই টাইপ করা, তবে ছোট করে লেখা আর ঠিক আছে, বই আরো বড় করে লেখা। ঠিক আছে, আমি পাঠিয়ে দেবো, হয়ে যাক, পরের দিন ক্লাস হয়ে যাক। ঠিক আছে, আজকে আমি এখানে করছি, আবার পরের দিন আবার এখানে রিপিট করবো।